Hi everybody, welcome to another video in Calculus 2. This time we combine section 8.6 and 8.7 together. So, iteration techniques pretty much. What we do in real life is a little bit different than what we do in this class, because later on, especially when you go to doing science or engineering integration, we can just use the advanced calculator. But what we do in this class is only when we use the calculator. This is the numerical method and only apply for definite integral. So we use a calculator. That is section 8.8 right after this. We don't use the symbolic method here. Right. And mostly the analytic method, we only do the standard method. We don't do a lot of table integrals. But before we start the section where we do a lot of integral, just want to talk about history in math, more like the applied math namely the calculator. So in 1972, the first handheld scientific calculator, it is of HP, sell for about $40. Right now you can get this at the dollar store, and pretty much the scientific calculator can do all the trig function, the log, exponential function, and pretty basic, pretty standard. And you said there's no big deal of this, but actually the big deal is it is in 1972 that is the first handheld scientific calculator. That is 3 years. I mean, the scientific calculator is invented after we built a rocket to the moon. Right, so before the handheld calculator, when we're trying to find the trig values or exponential function or log, we just go to look at the table. For example, e to the x, and then we like e to the third power, we just go and look it up on a table like this. Same thing for trig function. And the kind of the book that we use, that is usually called the handbook, and the handbook, but actually a very, very heavy one. Handbook for scientists and engineering. There's a lot of different publishers have something similar to this. And this one actually it is in 1961. Of course, that is way before the time of the scientific calculator. So that's why this is very popular in calculation. Of course, we have to have this book in order to do the calculation involving trig or log. Of course, the slide rule also work, but I think this one is a lot more accurate. Right. So that is, I think, about 1972. That's what I said about the scientific calculator. After that, we have the graphing calculator. I think this probably in the 1980s or 1990s we have a calculator. This one in the 2000s. Right. So, and probably about early 2000, there's developed what called a symbolic calculator. So something like TI-92 or TI-NSPI. So pretty much now the calculator can do integral, indefinite integral. So they will do, and they give you the answer. I'm going to show you some of the type of the problem that a symbolic calculator can do. Right. But if it is, we cannot do the integral before that. Also in this kind of handbook, there's called the table of integral. So when we see an integral that we don't know how to do, and there's some of the integral, then we just look it up, the values. I mean, look it up, and they just give the integral, and we just have to do that. And like I said, this kind of books are very common for all the engineering and all the scientists. So they have just integral of a lot of different forms. Right, so that is before time. It's just like 60 years ago. Yeah, about 60 years ago that we still have to use that. Now we don't. Alright, now, and also we need to recognize that there's some certain function that we just we cannot do it. For example, nobody can do this. Nobody can integrate this, and later on you should see the error function. Right, so that's the first kind. Also, we cannot integrate that, and likewise we cannot do integrate sine of x squared or cosine. And this, I think I spelled this right, Fresnel sine or cosine integral. We cannot integrate this, and also we cannot integrate I think this one is sine integral. Actually, I think it's in this book though. Yeah, sine integral in this form. The reason they give you the table because there's no nice formula for it, so we just have to have the table. Alright, and how do we calculate this table? Well, that's another story. Right, so I said those are the common integral that we cannot integrate. Alright, now let's just go to something that we can integrate. Sorry about all the introduction. I thought that is interesting. Alright, so now first one, find the area bounded by the function and the x-axis. So pretty much we're talking about this one, between 0 and pi. Actually, if you remember, we actually did this in the first section. So bottom line is we try to integrate from 0 to pi. That integral, the function above minus the function below. Right, so pretty much we do that. Right, now before I go any further in the section, I just want to mention that this section we focus on the technique, or what I call just the toolbox. In order to do a lot of things, we have to have some tools. The more tools we have, the easier we do out of. So this section we go over a lot of different technique and a lot of different tools, and I think that might be helpful later. Right, and if you remember, we did this in the first section, if I remember correctly. What we do is substitution will not work, because if we let u equal to the denominator, derivative of sine is cosine, and there's no cosine there to cancel. You cannot do that. What we can do is try to turn the denominator into one term. So what I do is multiply top and bottom by the conjugate of that. So how did that help? Well, a lot. Multiply the top, we have 1 minus sine x. The bottom, 1 times, just multiply it out. 1 times 1 minus sin x plus sin x minus sin square. Cancel out. And then we have 1 minus sin square. 1 minus sin square, that is cosine square. So sin square plus cosine square is 1. I'm just going to do that. So 1 minus sin square. Subtract this on the other side is cosine square. And we substitute to that. And then here we can split. Now, split the top, that is. Uh, 1 over cosine square, that is secant square. And this, if we write as sine over cosine, and then we still have another cosine, so put 1 on the top. So in that case, we have 0 to pi secant square. Sine over cosine is tangent. 1 over cosine secant, so we have secant tangent. Now, integral of secant square is tangent, and integral of secant tangent is secant. Go from 0 to pi. Right. So I have tangent of pi minus secant is, it is easier to evaluate if we use cosine. Yeah, so we write 1 over cosine instead of secant. And then tangent of 0 right. Tangent of 0 and tangent of pi, y over x is 1, 0, so that's going to be 0. So pretty much we have cosine of pi is -1. So we have 0, and cosine pi is -1, and cosine of 0 is 1. So pretty much what we have is -1 over -1, subtract 1 over 1. Tangent of 0 is 0, tangent of pi also 0. And so when we do all of that, I forgot the minus here. When we simplify everything, that should be 2. Right, just make sure it is correct, and we put integral from 0 to pi alpha y equal to fraction. By the way, the way to calculate the operating system that give us the print like this, I think this is only 10 years old. It's not. Back in the first time when we have the TI calculator, it cannot do this. And now the display is a lot more friendly. Actually, just the displays. In terms of calculation, there's nothing new. Right, so that's good. We have 2. Right, like I said, we only use calculator for definite integral. For indefinite integral, we just have to do it by hand. Right, something like this. Right, what can we do here? Right, so if we go back to section 8.4, when we have something under the square root, we do trig substitution. The reason that we do trig substitution because somehow we can combine this into one term. Square root cancel the square. So my point is try to combine this. I should say try to write this as a square, and then we can follow from that. Right, let's see. So the idea is we try to write this as a square because hopefully square root of the square that cancel out. But even though if we cannot do the square, there's some advantage come out of that. So first what we do is try to make a square out of this, or we call completing square. So we have x squared plus 6x. Right, what we're trying to do is to make this into a square. So if we need a square, we need to have 3 terms. Right, to make a square, we did this before. Take half of the middle coefficient, and then we're going to square. So half of 6 is plus 3. Square of that is 9. So if you just add 9 to it, you have to subtract 9 back to keep things balanced. So now the first 3 terms is the perfect square trinomial, and it can be written as x and that square. So the first 3 terms is that, and then minus 9 you can write as 3 square. Right, now instead of that, let's write the integral is equal to So remember, in the trigonometric substitution, when we see something like this, a variable square minus a constant square, that is secant, right? Again, variable square minus constant square. So actually we can let u equal to x plus 3, and after that we do the substitution. But in that case, we just let x plus 3 equal to secant, just right away. So the substitution here a little bit different. Right, so again, what we have is, let me just write this out. We have a variable square minus a constant square. So we're going to let u equal to a secant theta. Alright, so we're going to use substitution as a secant. By the way, we don't even have u. So in that case, we'll let u equal to x plus 3 and then all of that. So actually the substitution here is we're going to let that be u. But we're not going to write u. We'll just say let x plus 3 equal to a secant theta. So we let something more than just x be a trig function. That's perfectly fine. In that case, we move the 3 over. And then we can take derivative. At 3 here doesn't really do anything. Integral of secant is secant tangent. And then we move the d theta over. Right. Now, what do we have inside the square root? So we have x plus 3 square minus 3 square. X plus 3 is a secant, so we have a. Sorry, in this case, a is going to be 3. So we should put that 3. Yeah. Yeah. In particular, this type a is 3, so we choose u 3. Right. X plus 3 is 3 secant theta. Three square is 9. I just say 3 square, and then secant square minus 3 square. Factor out 3 square, secant square minus 1 is tangent square. Right. Now, I'm going to substitute this back into that. So now the integral equal to, inside the integral is 3 square tangent square. And the dx is this 3 secant theta tangent theta d theta. Right. Now, square root and then square that cancel out. We have 3 tangent theta. That square cancel with the square root cancel the square, and then we have 3 secant theta tangent of theta d theta. Right. So after 3 and 3 make it a 9. Tangent times tangent, so tangent square. and then secant theta. How do we do this? Actually, I think we did something like this back in section 8.4. So let me look it up on what we did on section 8.4. It's about trigonometric substitution. Right, found it, 8.4. Sorry, 8.3. Right, trigonometric integral. So we have power of tangent and secant. So here, if power of secant is even, so we look at this, power of secant is even, nope, we don't have it. If power of tangent is odd, don't have that either, so that's complicated. Luckily, I think we did this problem. This is tangent square and secant. So exactly, we did this before. And of course, that's followed by the integral of secant cube. So it's on page 37. Now note, so we just say see page 37. So this is where it will be helpful if you write on the note and then you can reference quickly. So in page 37 we have integral, that is section 8.3. We have tangent square secant equal to 1/2 secant tangent minus 1/2 ln secant x plus tangent x plus c. Right, so that's what we have. Right. This section kind of a review of what we did earlier too. Right, so according to that, in this example, the integral will be equal to, don't forget the 9. I usually make that mistake, and as I did that on section 7.5, when I have the constant, when I copy to the next line, I forgot that constant. So there's a 9 there. The integral though is equal to this. So we'll have 1/2 secant. We're going to use theta instead. Right. Now, what is secant and what is tangent? We do know that. Now we go back to this. X plus 3 over 3. X plus 3 equal to secant. So now if we want to solve for secant, so secant is equal to x plus 3 over 3. We don't need theta, so we're just going to leave it like that. Secant is 1 over cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. So make a triangle. Hypotenuse adjacent. So the opposite is going to be square root of x plus 3 square minus 3 square. By the way, that we did say it earlier, equal to x squared plus 6x. Now we need tangent. So tangent is equal to opposite over adjacent right? So we have secant and tangent. So we can substitute those two into the integral. So we have 9 1/2 secant is that, tangent is that, minus 1/2 ln x plus 3 over 3 for secant, and square root of x squared plus 3 plus 6x, sorry, over 3. Right. If we want to, we multiply 3 and 3 and cancel with this 9. Right. Then multiply the 9 over. So just one step to 3 and 3 give us 9 at the denominator. Cancel with that 9, so we have 1/2 times x plus 3 square root of x squared plus 6x, and then 9 multiplied here is 9/2 ln of x plus 3 over 3 plus square root of x squared plus 6x over 3. Actually, there's one more thing we can do, but I will do that in the next problem. Not exactly next problem, but some problem after that. Right, so that's what we have. Now we have another example here. Now this looks complicated. Right. Make a lot easier. Not a lot, but at least I will write like this. So have dx on the back. Right. There must be some kind of substitution. How about let u equal to e to the x plus 1. And we said they might not be able to cancel, and that may be the case. Right. This is one of the nicer, I mean, I'm not saying nice, but it's one of the typical example. It's a good review when we have this problem. Right, if u is that, then we take the derivative. E to the x is still e to the x. Now move the dx over. And then we divide back. Yeah. So we can do the substitution. E to x plus 1 is u, and then dx. Dx is du over e to the x. Right. There's a little problem. We have e to the x. In particular, we have x, and that is the problem. We have to write that in terms of u. Luckily, it's not that bad. If that is the case, then u is equal to e to the x equal to u minus 1. And we can substitute to e to the x. and we're going to write u minus 1 like this. Right, a little bit better. But that's not quite. If it is because of the square root, so if we have to take care of the square root, so let's just go one more step and do another substitution. I'm just going to use this. Let v equal to square root of u, or u to the 1/2. We take derivative 1/2 u to negative 1/2. Move the 1/2 to the bottom, u to the negative 1/2 to the bottom. Would turn into 1 over 2 square root of u, right? And then cross multiply du times 1, du is equal to 2 square root of u dv. And substitute into our problem. Square root of u, well, that is v. U minus 1, well, what is u? U, if we square both sides here, v square equal to square root of u square equal to u. So v square is equal to u. So here we have u, that is v square. And then dv. Right. By the way, I forgot. And then du, right? And du is this. Yeah, du. Now, and also that is equal to v. So this is equal to v. So this is equal to integral of 1 over v squared minus 1, and then the 2 square root of u is v. And they cancel out nicely. And then the 2, we can take it outside. Oh, but you know what? Let's keep the 2 inside. The reason we keep the 2 inside because this is just a partial fraction. Sorry. It's just a partial fraction. And then that would be not be expected. So integral of 2 over v squared minus 1. Very nice, right? And that is 2 over v minus 1, v plus 1. Right. Now, partial fraction. So I did mention that this problem is really interesting in the sense that it covers a lot of different things, especially the substitution here is when we do the substitution, we substitute, and even though there's x left, we can always take care of that. Even here there's the u left, but that's also v. So the substitution here, even though there's left with the original variable, but that variable can be written in the new variable. Right. Let's do the partial fraction. So this is simple enough. We can do it by hand without the calculator. You will see. So we start with 2, v minus 1, v plus 1. And there's two fractions of v minus 1 and v plus 1. So on the top we're going to have a and b. Multiply both sides by the least common denominator. So we have 2 equal to v minus 1 times v minus 1 cancel. We have a of v plus 1. And then plus v plus 1 cancel out b of v minus 1. Right. Typically we will multiply it out, combine like terms, but we're not going to do that here. What we do is just, as this another way to solve for the coefficient. Here we have v plus 1 and v minus 1. So what happened if we say, if we choose v equal to 1 or v equal to negative 1. Start with negative 1 first. If v equal to negative 1, we have 2 equal to, put negative 1 into v. That's 0, which cancel out. That is negative 2. So we have 2 equal to negative 2b. So b is negative 1. Next, we're going to let v equal to 1. The reason we choose 1 and negative 1, because if we choose v equal to 1, this goes to 0. So we choose something that make this equal to 0. If we have 3 variables, if we have 3 coefficients a, b, and c, we're going to need to choose 3 values for v. Here we have 2 variables, 2 coefficients to solve for. We only need 2 values. So we choose that equal to 0, and we choose that equal to 0. Now, v equal to 1, substitute in here, we have a, v equal to 1 plus 1, b 1 minus 1. Now that goes to 0. And this equal to 2 equal to 2a. So a is equal to 1. So when we have simple partial fraction, we're just going to do it like this. We don't have to use the RREF in the calculator. Bottom line is we'll continue on this integral. And that's also why we keep the 2 inside, because if we have 1 here, that's still the same. We just do partial fraction. So the constant there doesn't really do much. Right, bottom line is from that integral will be equal to, we're going to write in this form, (1 over v minus 1 minus b is negative 1, so let's say negative 1 v plus 1 dv). And we will split the integral, or we will split I should write like this instead. Right. Now, section 8.5, like I said, this section is a good review of all other sections. Section 8.5, before we do the partial fraction, we review the integral. And so integral of 1 over x plus a is going to be that. So in this problem we have ln of v minus 1 minus ln of v plus 1 plus c, and then v is square root of u. And v is square root of u. Now, also, when we subtract the two logs, we can write this as a quotient. So square root of u minus 1, square root of u plus 1. And then u is e to x plus 1. So bottom line is we put this together and we have ln of square root of e to the x plus 1 minus 1 square of e to the x plus 1 plus 1 plus c. Alright, so that's how we do it. However, I actually check my work and then I put in the calculator, not calculator, I put in the software. It's called Maple. That is the computer software. This company actually does the symbolic math. One of the first company that does it. So actually it can integrate, and when I put the integral, it gives me -2 arctangent hyperbolic tangent so this is hyperbolic tangent in inverse. Or if we use the calculator, I mean if we use the other notation, this is -2 inverse so this should be somewhere in the calculator. Let's see if that is the function. No, I think it's under catalog and tangent. So alpha, where's the t? Yeah. Oh, the calculator frozen, sorry. At yeah, so that is that function. Anyway, like I said, because calculator, we did not learn about this function, so that's why we didn't write the answer in that form. But that's what the calculator or the computer give us. But we did this by hand, and that's what we have, which is perfectly fine though. So like I said, if we have the answer from the calculator, it might be different than what we have, but in terms of the function, it should be still the same. If you graph those two functions, they're only different by the constant c. Right. Next, I'm not going to do this problem. Just going to get the idea about partial fraction. Like I said, this section we more focus about the technique than the end result. That's what I should say. Right. So x cubed plus 8. That is the difference of the sum of 2 cubes. Just going to write that formula again. If it's minus, it's going to be this. If it is plus, so the first sign will be the same, the second is opposite, the last one is always positive. So those are the sum and the difference of 2 cubes. So substitute in here, we have x plus 2 and then x squared minus 2x plus 4. Right, so I move the dx to the back. And if you do this, actually I put in the calculator, not calculator, in the computer software, in the Maple also, and this is what I have. Negative 1 over 24 ln of x squared minus 2x plus 4. Actually this one is positive, so I just need the parentheses. Minus 1/2 ln of x plus 2 and plus 1/8, 1 over 24, and then 1/8 ln of absolute value of x. Right, so that's what I have from the calculator. Now I leave the whole page for that because I want to focus on something else. So what we have up to this point, we have the partial fraction. What happens if we have something like this? I'm just going to make up an example. Right. Consider something like something like this. So what is the difference of this one and that one, and what is the difference in partial fraction here? So in real life we perfectly sometimes we might have something like this where degree on top is greater than the bottom. So in this case we call it improper fraction, but improper partial fraction. Improper partial fraction. We could have x to the 4th or any higher degree, as long as the degree on top is greater than or equal to the bottom. That is improper partial fraction. In which case what we do is we have to divide. By the way, let's just write first. Improper partial fraction is when degree on the top is greater than or equal to degree at the bottom. In which case we need to divide them first. But since I don't want to do the division here, what I do instead is this technique. Right. Since we have x cubed plus 8 at the bottom, why don't we make it on the top? And if we have that, we cannot just add 8 without subtracting 8. So we have x cubed plus 8. Just keep that in the parentheses by itself. And then minus 8 minus 2 is minus 10. So this is as good as we dividing them. And then we will split. And x cubed over 8, so it's going to be 1. And we split the integral. So my point is, when we have improper partial fraction, we need to divide them first and then split it out. And then what we have remaining here, this is the standard partial fraction. So, yeah, rather than doing this problem, I just want to mention that sometimes we have the degree on top is bigger than the bottom. In that case, we have to divide them. So these two sections, 8.6 and 8.7, cover a lot of things that we did not cover in those sections. Kind of a very good review by itself. Right. Next we have this one. Now this one, earlier we have something similar to this, right? Yeah, that. And we did let u equal to e to the x plus 1. Yeah. This one we have e to the 2x. Slightly different. We won't be able to do that. But just make things a little more interesting. Actually, this should be minus. Actually not interesting, it's just a typo. I meant to write minus. Alright, now what substitution do we have here? So, by the way, we won't be able to use the typical substitution, because if we let u equal to e to the 2x, that's not going to help, because the derivative of that is the 2e to the 2x does not cancel with this. What it does cancel is we're going to make very subtle change. E to the 2x can you write as e to the x square Why is that though? Notice we have these properties of power to another power, right? That's easy enough. So in this case we have e to the x and then to the 2. We multiply the exponent together. So that's why we have e to the 2x. Right, so that's good. Now when we write like this, we're going to let u equal to e to the x, because the derivative of that is e to the x. as well. So that's good. So the substitution here is e to the x and not e to the x, e to the 2x. So let u be e to the x. Take derivative. Same thing. Move the dx over. And in some book they say we have e to the x and dx. That's going to be du. Yeah, we can just do that too. But usually I'm just going to solve for dx. We have du over e to the x. And I just substitute into this dx. Right, so we have integral e to the x still there, right? Don't write u, we don't need that. It is u, by the way. Here we have e to the x square. That I want to write as u. By the way, this is also u, e to the x, and e to the x is also u. If we want to, we can just write like that. But I only focus on this e to the x here. And then dx is du over e to the x. The reason I said it doesn't matter because they cancel out. Alright. Now, and for this one, of course, that is a trig substitution. So here we have u squared minus a squared. Variable square minus constant square. So in that case, we let u equal to a secant theta. So in this example, we're going to use the substitution. Let u equal to a, which is 2 secant of theta, and then we continue derivative. Of secant is secant tangent. Move the d theta. D theta. Right. Now, substitute back into our problem. Before we do that, as always, try to write u squared minus 4. U is 2 secant theta. And that gives us 4 secant square minus 4. Factor out the secant square. Secant square minus 1 is tangent square, so we have 4 tangent square. And that we can write 2 tangent theta square. Right. Now substitute that under the square root. Now the integral will continue equal to 1 on the top, square root two tangent theta square du is this. Secant theta tangent theta d theta. Right, square cancel the square root, undo the square. That cancel out, and we just have tangent. Now integral of tangent is sorry. That cancel the tangent and left with the secant. Sorry. That was too obvious. I should pay more attention to it. Because it's almost there. We do cancel the 2 though. So we have secant left. Sorry about that. And integral of secant is the ln secant plus tangent. Right, need to know what is secant and what is tangent. We have secant from there, if we can solve for it. Secant is u over 2. Secant is reciprocal of cosine, and cosine is opposite over hypotenuse. So we have hypotenuse over adjacent. Yeah, that's 1 over cosine, and cosine adjacent over hypotenuse. So hypotenuse is u, adjacent is 2. This will be u square minus 2 square, or square root of u square minus 4. Right? Oh. Sorry about that. That is secant. Right. The 2 cancel out. Right. Now, we have the opposite is equal to that. So tangent is opposite over hypotenuse. I mean opposite over adjacent. And we have tangent and secant. Kind of like the problem we did before. So it's equal to ln of secant theta plus tangent theta now we know u is e to the x, and here we have e to the x squared minus 4 over 2. I hope there's something wrong with my calculator computer. I don't know what, but I hope that it's okay. We have e to the x over 2, and e to the x squared is e to the 2x. We talked about that earlier. Right, so that is what we have. Right, I actually put this in the calculator to make sure that everything works out perfectly. By calculator, I mean in Maple software that I used. Put that in the calculator, in the Maple software, And when I integrate this, I end up with ln of e to the x e to the 2x and I say, is there a mistake here, right? Where's the 2? Luckily, it's no mistake here. The only mistake in this problem was that, but we already fixed that. Anyway, so this is our answer, right? What happened to the 2? Right. So this is what happened to the 2. Just to make sure the calculator works. What happened to the 2 is this. Now if I continue from the integral, and I will factor do the common denominator of 2. Now what we see is ln of a quotient. What we use is this properties, ln of a product is the sum of the ln of the quotient is the difference so we will split even with absolute values now, don't worry, we still split e to the x minus ln of 2 plus c. Now what we can see here is ln of 2 is a constant plus c is a constant, so all of this is still a constant. So that's why we can just say this equal to ln of e to the x plus, and then minus a constant or plus a constant, doesn't matter. Just say add the constant. I'm going to just spell out the constant because that is different than this c. So when we write the answer like this c is different than that c, but in general those two will be the same thing. They're only different by a constant, so perfectly fine. So as you see, the calculator even know how to simplify the problem. So this is how far we can go. Right, so that's what we have on that one. Right, so a little creative substitution. We don't let equal to the whole thing. We only let u equal to e to the x because that's simplified nicely. And then we have the trig substitution. After that, if we want to, we can simplify this using those properties. Right, next. Integrate this. We did a lot of this, so I'm not going to say this. But like I said, usually when we have something under the square root, we try to do the complete square. But complete square, usually we have the x squared x or something like that. This is already completed, the square already completed. So we're going to say 2x square plus 3 square because they already is completed in terms of squares. So what we have here is u square minus a square, and for that we're going to let u equal to a, that's a plus, right? A tangent of theta. So if we want to do this problem, is we're going to let u equal to not u, there's no u here, u is 2x, so we just go ahead and say 2x equal to a tangent of theta. So in these two sections, what we actually do, the trig substitution, we don't just let x equal 2, we could let 2x equal 2, and earlier we actually where was that? Here. We let x plus 3 equal to the trig function. That's perfectly fine though. It's not always x. It could be something a little more complicated. Right, and then the rest will be similar. I'm not gonna spend time to do that because that's pretty standard trig substitution. What I want to focus on is what we call the table integral. So these formulas I copy from this book. Hopefully I do that correctly. Like I said, the technique, we focus more about how do we do the problem than the answer itself. So, for example, when we look at this problem, we have to compare to the right form. Right? So first, the right form here we have u squared minus a squared, and the top is 1, so we have to turn it to exactly the same form. So when we use the integral using the table, we have to convert to the right form, and then we can just use that. So if we have x squared, that will be perfect, but it's not. There's a 3, so take care of that 3 first. If I want to get rid of the 3, have to divide by 3 on top, divide by 3 at the bottom. So 2 and 1/3 on the top is 2 over 3. The bottom 1/3 times 3x squared, that will be x squared, and 9 minus times 1/3 minus 3 dx. Right? Even though all of the color code, sometimes I forgot that constant. And now we write x squared and 3 square root of 3 square dx. Now it looks exactly as that form. So it will be 2 over 3. Right. Once again, sorry about the problem in section 7.5 where I forgot the constant. Sometimes I forgot to write that constant in front. Right. Now for that integral will be exactly as that form. So be 1 over 2 times a. So let's just write a is square root of 3, and then u which is x. So 1 over 2a, 2 over square root of 3, that is a. And then ln absolute values u minus a u plus a. Two and two cancel out. 1 over 3 square root of 3 x minus square root of 3 x plus square root of 3 plus c. Right. So that usually if we don't know how to integrate, try to look it up, and maybe there's a formula for it. The reason that we don't have this kind of book anymore because most of those are online. Having said that, we don't even look for the formula anymore. Like I said, if we type it in, a powerful symbolic calculation, symbolic computation, it pretty much is integrate for you. So in the future, I expect that integration is just like a multiplication, kind of the problem that we can use the calculator for. We don't even need to do that. But I still think that's interesting to do this by hand. Right, so next we have this problem, and I just put this formulas there because that look nice, but we don't even need to use that at all. Right, here what we have is the square at the bottom, but when we have the square at the bottom, we don't have anything on the top. The top is just 1. So we have to make some subtle adjustment here. So we have something over that and something over square. This we have the square, but the top is not that. If it is constant on the top, it's perfect, but it's not. So we used this trick a few times already. It's just like dividing, but we're going to manufacture the plus 4. Because when we split it, that will cancel with the bottom and we don't have the square anymore. So we cannot just do that, right? Minus x minus 4. We cannot just minus 4 without adding a 4 to it. So now when we multiply it out, negative x, negative 4, plus 4, minus 4 plus 4 cancel out. So that's good. So this is plus 3. And then we have x plus 4 at the bottom, square dx. So even though we have all the formulas, it's nice that we still need to try to turn into exact form that we have. And so we split this. Four plus 3 is 7. Right, cancel that out and take the negative outside. We just have x plus 4. We can take the 7 outside. Right, now we can use the form. Right, ax plus b and ax plus b. So in this example, a is 1 and b is 4. So when we have a is 1, b is 4, put it back in here. Let me zoom out. It's not enough. Yep, that better. By the way, this is just ln of x plus 4. We actually did this before, right? So this pretty much just like the problem, a kind of like partial fraction, right? But we're just going to use that, and plus 7 times 1 over a is 1, ax plus b is x plus 4. So that's what we have. Minus ln of x plus 4. Yeah, just say, just like the form they have, which is this, plus 7 over x plus 4 plus c. Right, so the problem with the table integral is where we have the formula in the table, we have to turn our integral into exact form into that. In that case, we can use it other than that, like that. Even then, when using the table, it's not very common anymore. In the future, the integration, I think it's just a given, just a calculator do that. And then you said, I did mention that sum of the integral, we cannot do it. So in that case, there's a way to handle those situations. But what we did in this section is, it's a good review of everything in chapter 8. Actually, we didn't do much of the integration by parts. We have substitution, trig substitution, partial fraction, and then a lot of technique nice and there. So this is just these two sections just cover something that we did not cover on those sections, and so in that sense it's rather important. Right. So there are a lot more to this that I want to cover, but I think that will be enough for section 8.6 and 8.7. See you in another video. As always, thank you for watching.